Welcome to today's webinar. The topic today is lateral stability with timber shear walls in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, newsletters, customer projects, and so on. I will be the moderator today and I will answer your questions during the webinar. My colleague Gerhard Rehm will be the presenter today. He's the main responsible person for the development of the timber design and multi-layer surfaces add-ons. You can ask questions when you click at the button with the question mark, then enter your question in that field, press send, and I will receive your questions, and I will answer you. The other way is to watch the entire webinar and then write an email to info@dlubal.com. Okay, that's for the moment all from my side. I hand over to Gerhard. Gerhard, you can start.
Okay, thank you, Andreas, and a warm welcome from my side as well to today's webinar about lateral stability with timber shear walls in RFEM 6. On the first slide, you see the content for today's webinar. In the beginning, we check out a few theoretical things before we compare some common stiffening method with our FEA approach in RFEM 6. Next step is the design of timber shear walls, but this has not a main focus today. We talked about timber shear walls and its design already in a previous webinar. And then at the end, we will take care of effects of wall openings and walls with different stiffness on lateral stability before we end the session with an outlook. Okay, so I talked about this previous webinar. So when we go to our website, dlubal.com, then go to news, go to webinars, and then you can search for, or you can activate some filters, complete it in English, and then maybe it's first to, activate the checkbox for Eurocode 5. And you will see all timber related webinars, what we did in the past. And here is this webinar, what I'm talking about. So here I have showed and demonstrated everything about the timber shear walls in RFEM. I show how to create the shear walls, show how we define everything and so on in detail. So I will skip this part today. I will not spend so much focus on how to create the walls. I assume that, you have watched it already, and if not, you can do it afterwards. Okay, then let's go back. Okay, first let's talk about lateral stability. It's the measure that ensures the stability of a building against horizontal forces such as wind, earthquakes, lateral thrust, or other loads, for example, impact. You see it in a nice way how this could work without any bracing system. It's an AI generated image, but it gives you an idea how how the buildings would look like. Yeah, of course, nobody would build it like that, but it's really common, especially in the US, for example, where you do not prefabricate the walls. Yeah, so you pitch up everything on the construction site. And if you really forget the bracing, then maybe in a few hours it will look like that. Yeah, of course, this is not our aim, but our aim is the building must be designed in such a way that horizontal deformations are minimized. It's clear so far, I guess, and it's clear to everyone who's attending this webinar. But I just want to give you an idea of what's about today's topic. So in other words, our lateral loads needs to be covered by the building and needs to be transferred to the ground. to our foundation. Okay, here are a few minimum criteria for lateral stability. So we distinguish between with roof or floor diaphragm and without. So when we consider a floor or roof diaphragm, we need at least 3 wall panels in 2 different directions with a common intersection point. So we have 3 walls, and we have here 2 intersection points. It's clear that this will work. Without any diaphragm, we need, of course, 4 walls, of which a maximum of 2 intersect at a single point. But watch out, when we have no diaphragm and we have long buildings, that the deformation of the wall along its length can be controlling. So for small buildings, yes, this will work, but for bigger buildings, especially in timber where we do not have any fixed supports, this can be challenging. Okay, then a small first example. It's about a carport with a roof diaphragm. And here on the left side, we see the ideal case. And the ideal case is when the center of rigidity is located on the line of action of the resultant force. So we have no eccentricities here, and we have our force F, and the left and the right wall will cover half of the force, which is clear. Yeah, but the most common case looks different, that's clear, because the center of rigidity is eccentric to the line of the action of the resultant force. So that means we will get some moment and torsion of the building. In this case, all walls participating in the building's bracing. So that means we will not get only the action and reaction force, but we will get here this force as a result from this moment. Okay. Next slide. I guess you know all these images, but it's about the bracing systems. So here on top, we have our bracing systems, which will work quite good. Here with the core or at the exterior walls, we will have some bracing. That's clear that this is a nice system, but of course, it can work different as well. Especially when we have a look at this image here on the longitudinal walls, they forgot the bracing. Of course, this will not work. The remaining 4 images, it is about buildings with problematic bracing systems. So here on this image, we have the core or the bracing system at the edge of the building. We have less load on top from floors, for example. That means we will get really high tension forces on the hold downs. And of course, because of the eccentricity, we will get high deformation because of the torsion. Same here or here or here on this open core or open section core, whatever you call it. Okay, so that's clear so far, I guess. I don't tell you any new things, but just to remind you, to fulfill the criteria. Okay, then let's come to today's example. This example is a result of a book from François Colling. It's a German book. I'm sure there will be some literature also in English, but I'm not so familiar with it. So of course I'm German and I'm familiar with the German literature. But this example can be found in this book. And here Mr. Colling is calculating the forces on the walls and also is doing the design check. And today we will compare his results with the classical calculation compared to our FEA calculation. Okay, let's check the building. We have a building with 750 by 8.75 meters. We have a few walls with a wall length of 2.50 meters, and here is a wall with 1.25 meters. You see we have the center of rigidity eccentric to the center, and we have some lateral load as a result of wind and thrust forces as design load here. It's given by 603 kilonewton per meter. Okay, then the question is how we can deal with it in our RFEM software. Okay, so the question is how can we perform such a bracing calculation using frame analysis program or FEA program? So in the beginning, I show you some simplified method to verify the results from Mr. Colling. And for this simple example, we use members to model the diaphragm. Okay, so I will add some rigid members here for the walls, so these rigid members will represent, I select the line. So these rigid members will represent the walls. Here we go. So I assign a rigid member to these lines. And now, of course, the walls or the diaphragm is not closed. Yeah, we need to have a closed diaphragm to define, to distribute the lateral loads to our supports. Let's see. So that means we need to also give some stiffness to the diaphragm lines. I will do so by using a rigid member, but to distinguish in colors, I will use a coupling member rigid, which is the same by default as the rigid beam. Okay, so now we can distinguish between what is a wall and what is no wall. Okay, so we will apply our lateral load. So I've created a load case already without dead load, and our lateral load was 603 kilonewton per meter. I will apply it here at these members. Okay, and now we need to think about timber framing. Yeah, so when we think about how the forces will be distributed to the walls. Yeah, when we think about maybe, for example, we have two walls. So I will copy out the walls here, and let's assume this wall is 2 meters and this wall is 1 meter. And we will apply a total load of 3 kilonewton. In timber framing, we assume that the stiffness of the wall is proportional to its wall length. So that means when we apply 3 kilonewton on a 2 and 1 meter wall, we will get as a result this wall with 2 meters gets 2 kilonewton, and this wall with 1 kilonewton with 1 meter gets 1 kilonewton. It's different than CLT or, for example, concrete or steel. Yeah, but because of all these components which I showed in the first webinar, we assume that the stiffness of a timber frame wall is proportional to its wall length. And this helps us in a simple way that we simply can define some supports, nodal supports here at these wall locations. So I have defined it already. So we go to types for nodes. And as you can see, I've created some springs in X and Y direction, and I used here 1,000 times its wall length. So in this case, we have a stiffness of 2,500 kilonewton per meter, and I will assign this to our walls, which are located in X direction. So it's this wall, and that's it. We have Y direction, so it's this wall and this wall. Okay. We have X and Y direction, it's this one and this node. and we have only y direction, only x direction, but here we have less stiffness because of the wall length. Okay, and that's it. That's it actually. Yeah. So we simply run the analysis for this rigid diaphragm, which is supported by nodal loads, which represents the walls. Okay, yeah, sorry, I forgot. Yeah, of course, we need to connect also this wall to this diaphragm. Sorry, I forgot. So here we go. And let's start again. So the result should be, of course, nodal forces. Let's check these nodal forces. Maybe we'll hide the supports, and I will make a screenshot of it with the result. And now let's go into our PowerPoint again and compare it with our result from the book, which was calculated, with analytical solutions. It's clear, but when we compare the results, we get 30 kilonewton, 13 kilonewton, 6.5, 6.5, 14.9, 2.9, 2.9. So as you see, the result matched perfectly. Yeah. So this is a simple and easy way to do some lateral stability calculation for timber shear walls. But of course, the big problem here is the deformation, because we have randomly defined some spring constants which are not representing the real stiffness. So in this case, we cannot deal with the 7.4 millimeters. But what you can see here is the rotation of the building. Because the shear here, the center of rigidity is eccentric to the center of the load. And of course we will get some torsion. Okay, so that's the first way to do it, but of course this is not our aim. We will continue. For this we will delete all members. Here we go. We don't need this line, and we also do not need this node here. Okay, and of course it would be nice to see any 3D graphics of the building. Of course, this can be also be done by some members and effective stiffness of the members. So this is also a common case. We will not use any members today, but we will use surfaces. Okay, so to distribute our load, so maybe we can define a new load, in this case a new line load 603 to all these lines. Okay, of course, first I need to define some diaphragm. In this case, I will deal with surfaces. So in this diaphragm should distribute the forces to my walls. In the classical hand calculation, you assume a rigid diaphragm without any bending stiffness. And the same I will do in RFEM. So I create a new thickness. And to do so, I will use a thickness type stiffness matrix. We need to define some bulk density, but we don't care about that load at the moment. So it means we need to fill the stiffness matrix elements. So bending stiffness in x direction, I cannot leave it as 0 because we need to define it in a with values. So positive definite stiffness matrix is required. That's why we use a small value. I use simpler value of 1 for bending stiffness in x, in y, and torsional stiffness, same for shear stiffness in x, shear stiffness in y direction. And now we need the stiffness, the rigid stiffness of the membrane stiffness elements. Of course, we cannot enter infinity here, but we will simply use a really high value. I will use 1E11, and the same for the Y direction, and the same for the in-plane shear stiffness. Okay, so that's it. We have to find our diaphragm or our thickness, and I will assign it to my boundary here. Okay, perfect. So now we can define the load in X direction. Okay, here we go. Perfect. So I will switch into 3D and I will create the walls. So I will select all the lines where we have walls. Right click, extrude into line into surfaces. So we need a new thickness. So I will use stiffness matrix here as well. Okay, I cannot leave it. I want to rename it. So here we say walls. And for the walls, we do the same, or maybe it's easier to simply copy this one. And then, so this is the diaphragm. And these are the walls. Okay. So for the walls, we will do exactly the same. The only thing what we need to change a bit because of numerical issues, we need to reduce the stiffness of the walls. We don't care about the stiffness of the walls for now. Yeah. So we simply use in this case E1E and 6. Yeah. So it's a kind of stiffness. It's not really high. It's not less. So it's something in between. I don't care about at the moment. Yeah. So, okay, and we extrude it in C direction by, 2.70 meters. Okay, yeah, and that's it. So what we will do now is we will apply some nodal support, line supports. Here we go. And that's it. We run the analysis. And then let's check the forces, how they will be distributed, hopefully in the same way like in our simplified approaches. Yeah, same deformation. I don't care about deformation. We haven't defined the correct stiffness, so we cannot check any stiffness in this approach. But what we can do is we can, yes, I did, sorry. I have not deleted the nodal supports here on top. Nodal supports, delete assignment, yes, okay. And of course, I expect the same results in this case, like for, the simplified methods. Okay, so what we can do, it's already defined. I did check the actual distribution, so that's why I've activated this actual distribution of the support forces. I activated simple the info and check only the sum, and then you will see, or you will get directly this plot here. So maybe I can switch off types for lines, and we will do the screenshot again. Okay, go here to our slides, and then you will see directly perfect. Yeah, it fits nearly perfectly. Of course, there will be some difference in the second decimal place, but we don't care about. Yeah, so it's clear. But it looks good. So in a nice and simple way, we get our forces for the design of the timber shear walls. Okay, but would be nice to also see the deformation. Yeah, as I mentioned already, here we cannot check any deformation. This will not help. Yeah. So what can be done, or what is done in the past? Yeah, in the past it's still used, but you can calculate the stiffness of each wall by this mentioned component. So I've mentioned it already in my first webinar, where we have different parts of the deformation, yeah. And based on that information, sorry, it's in German from an Excel sheet, we get, as a result, we get the stiffness, yeah. And of course, all walls have the same length with 2.50 meters, and therefore all walls will get the same stiffness. Of course, not wall A2. Wall A2 is only 1.25 meters and has a bit less stiffness. So we will deal with that. That means we will simply create a copy for comparison. Okay, create a copy. And now I will check out the stiffness again. Maybe I'll activate this mode. Okay. So what I need to do now is we need to assign the real stiffness to these walls. Yeah, this is another method. So in this case, I will create a copy again. Walls 2.50 meters. And what we need to change is we need to change the D88 stiffness matrix element, which is the in-plane shear stiffness, and the value was 1831.79 for 2.50 meters long wall, and again a copy with the 1.25 meters long wall. It had 1509.20. Okay. So we will assign the correct thicknesses. And let's do it again. Let's run the analysis and compare again the results. Okay, let's check the forces. Okay, what's happening? We get nearly the same values like for our simplified approach. Yeah, of course, the wall is a bit weaker than, so it's weaker than the other walls. Therefore, the forces will get distributed more to the center wall here. But in summary, you can say the forces are identical. But the advantage here in this approach is, of course, we get the deformation. Yeah. And this is, of course, really helpful, especially when we need to check the deformation. Yeah. But what is the problem, or what is now the problem with this approach? When we go to PowerPoint again and we do some comparison of the calculation methods. So when we check the construction, for example, regular floor plan across all floors, this can be done with all approaches. Yeah. When it comes to different stiffness per floor, yeah, so it works, but you need to do some extra things, some approximations and so on. With FEA approach, this all works fine. With FEA approach, I mean when we use an approach where we do not calculate effective stiffness, what I did before in this example. This is our beam panel FEA approach. For example, okay, not so common in timber construction when you have rigid columns. Yeah, challenging to consider this in the classical FEA, in the classical calculation method. Then let's come to walls with different stiffness. Yeah, so this is not impossible, but yeah, it is possible with really much approximation, but I do not recommend it. That's why it's red here and not yellow. Or for example, consideration of downstand beams. This is not possible in the classical theory. Yeah, different wall heights. Yeah, this is also, or not so, it's not so uncommon, yeah, to have different wall heights. And of course, this needs to be considered, especially when it comes to split level constructions. Yeah, this can be also only checked in the FEA approach. Then the most important thing for me, walls with openings. We will come to this later. Yeah, in the classical theory, we cannot consider openings. Also, nonlinear effects are possible in the FE approach. So when we think about the US standards, they use nonlinear slip curves. So I hope we will get some nonlinear slip curves in the Eurocode as well at some point. Or when the diaphragms has different stiffness, for example, or different parts with different stiffness, this can be checked only with the FEA approach. And also the interaction between walls, corner or T-joints. Okay, so that's why we have our beam panel approach, and we will compare now the approach with the classical approach. Maybe one thing before we go to the beam panel, I want to show you something about our building model add-on, sorry. As you know, maybe we have this building model add-on. For this one story, maybe it's not worth to activate it, but of course for multi-story buildings this will help you a lot. We can also combine it with the beam panels afterwards, but I want to show you is how to create here the stories, so I will do so. So the first story was at top 0 C direct location, and here it's 2.70 meters, and here we use a rigid diaphragm. So with the building model add-on, we will not do this classical 3D calculation, but we will distribute the forces here via this rigid links. And the advantage of this method is mainly with multi-stories, but for our demand, we want to check and prove the center of rigidity. So we check according to our book, it's at a location 2.81 meters and 3.39 meters. And when we go to the calculation here and we check the results of the building add-on, here we see the center of rigidity at 2.81 meters and 3.39 meters here at this location. Now, where is it? Here we go. So this has been proved as well. Okay, good. Then let's go back. We don't need this building add-on, and we also do not this approach with the rigid walls, but we keep this one here with the defined stiffness from this Excel sheet. Okay, so let's create another copy, and now we will check out our approach, and we will see the advantages afterwards. Okay, so to do so, simple select all walls, and now create a new thickness. You can create here the beam panel, and you can define all your studs, your sheathing, your fasteners, and so on. I will not do it today. I simply use my template. So I've saved the template already. I load this template, beam panel 6x12, 18mm OSB. Click OK, and all data was overtaken. Okay. And that's it. So we run the analysis here again. And then let's see how our beam panel approach will correspond with the simplified methods. Okay, maybe before I will activate this beam panel mode to see all the studs, all the rigid links, which connects our sheathing with the members and so on. And I forgot maybe one thing. It's not so important, but at least we should take care of it. So at the moment, I have to find beam panel, my sheathing at -c direction of the local surface axis, in -c direction. So the OSB should be inside. So when we check local axis system, yeah, here it's in -c direction, that's fine. But here the OSB is on the outside. That means I will reverse the local axis system to get the C axis to the outside. Okay. Hit the enter button to simply repeat the last command. Same here and here. Okay, top view, C axis shows in, yeah, to the outside. Okay, then again, so we'll check out how the beams are modeled, and we see this line hinge, and this line hinge here has defined the stiffness, yeah, depending on the approach, on the code and so on. And yeah, that's it. So let's run the analysis again and check out and compare the results. So everything is inside RFEM. We don't have to use any Excel spreadsheets and so on to calculate some effective stiffness. When there are changes, yeah, you need to redo everything. So this is actually the great advantage here. Okay, we don't need to see the axis system. And when we check, yeah, the forces, you will see they are quite similar as well. 15.2, 15.26, 2.7, 2.6, 18.4, 18.3. So all is good. Yeah. And here it has been proved automatically as well that, yeah, the stiffness of these shear walls are proportional to the wall lengths. Okay. So then it's all about clear from load distribution side. Let's check the deformation. Okay, so deformation here we have 11 millimeters by 9.6 millimeters. And yeah, in the stiffness for the left side, for the walls, we have also considered some semi-rigid, we have also defined some semi-rigid hold downs stiffness, yeah, which is included in the overall stiffness of the surface. But here we have simply used this linear supports, yeah. And with this linear supports, yeah, we have no hold downs defined, yeah. So what we can do is, of course, this we will do later, or yeah, shortly, we will define the hold downs perfectly, yeah. As a simplification, it might be enough to yeah, consider the slip inside the line supports, yeah. So for example, in this case, you could simply switch this to partial activity as a simplification, yeah. And for the negative zone, maybe define some slippage. In this case, I assume, okay, before the tension will be covered, there is a slippage of 1 millimeter, which is approximation from the hold down. So this is a realistic value. We could do so. And then we can rerun the analysis again and check about the results. Of course, now it's a nonlinear analysis. And yeah, that's always maybe a small issue because we have used the slippage with really hard branch. So maybe we should soften the branch a bit by defining some diaphragm. So I see it's not really converging. Maybe not so good. Maybe, yeah, let's wait until we reach 100, but it's definitely some local issue. But when we check the deformations, yeah, okay, it was not converging. Maybe we should not trust the results at all. But maybe it would be better to, yeah, define some stiffness here. Yeah, to get a softer branch. Okay, sorry, I didn't want to check it here. We had 11 millimeters here on the left side. So hopefully it's converging quicker and yeah, perfect. So we have 11.4 compared to the 11 because, of course, I did not want to change the stiffness here because, yeah, we have the deformation from the hole done already in the surface. Yeah, but as you can see, this is a simplification. Now we will do it right. Okay, let's go undo. Here we go. So what we will do is we will, maybe not again, we will create a new line support. And in this case, it should fail under negative PC force. And now our compression is covered. Yeah, now we need to define the hold downs. So for that, I will create a visibility of members with specific material. Here we go. And we get rid of this rigid links. I will select all edge studs. Here we go. So in the future, there will be a function which automatically creates these hold downs, but at the moment we need to do it manually. Okay, and now I will create a new nodal support, and we take care only about the tension force. So we will let the support fail in positive direction, and we will have a stiffness of it was 20,713 kilonewton per meter. Okay, and now we will assign this to our bottom nodes, not to the top one. Okay, so that's it. Let's run the analysis again and check the results. Okay, so here we go. We compare 10.7 by 11 millimeter, which works really good. And also the support forces. Okay, I did a small mistake. Sorry, wait a minute. I did not set it to local axis system, but global. We should do local axis system to see the reaction along its line and not according to the global axis system. Again. And then let's compare the results. Here we go. Okay, so we get 13.5, 13.5. So it matches perfectly. Yeah, of course, this is a simple structure. Yeah, without any special things like openings and so on. Yeah, I would expect to get exactly the same results. Yeah, but here everything stays inside RFEM and not with some Excel spreadsheets and so on. Okay, so here we have deformations, we have checked the support reaction. Yeah, all is good so far. What we didn't check is we didn't compare the beam panel design or the shear wall design actually. For that, I will go, or maybe let's check first the anchor forces. So I will deactivate the deformation and I will activate the nodal support in C direction. And so maybe we can do it by using some generated visibilities. In this case, I want to check nodes with supports and lines. Sorry, here we go with supports. Here we go. Okay, no types and no lines. Okay, so and here you see we have our forces to design our shear anchors, and here we see the hold down forces. Yeah, so it's up to 20 kilonewton. Yeah, not really less, but we will be able to fix this hold downs to our foundation. This is still possible with these forces, and you see perfectly the force on the hold downs. You see perfectly the shear flow to design the shear connectors. Okay, then we remember maybe one value. Let's remember this 15 kilonewton here for this shear wall, because we want to design the shear walls now and compare it to the literature. So I will cancel the visibility and I will undo everything until we reach the linear supports again. Here we go. And I will run the analysis. So we have in memory the 15 kilonewton. Is it possible to determine it also with linear supports? And yes, it is. So what we can do is we can simply right click this support, go to a result diagram, and then activate the C direction. And you see here the tension and compression forces. Simple create here a smoothing range from 0 to the center like that. Okay, and you will see you also get as a result for this area the 15 kilonewton, or you can shift it a bit also here. You will see that's also the expected value which we have calculated from the nonlinear analysis. So it depends always what you want to have, and of course it's about calculation time. That's clear. Okay, so what we still miss is the design of the timber shear wall. So I will run the analysis here for the shear walls. Okay, sorry, there is some stability analysis activated for this CO1. I forgot to deactivate it in the template. Okay, so what we see here is we see our ratio from the design check. So I have deactivated beams and sheathing design check for now. I don't want to check it with FEM based calculation. I have only lateral loads, so I don't care about the gravity loads for now. But what we see is we see our design check here. Let's have a quick look what is done. So of course we calculate the Johansson equation, we check the resistance of a fastener and compare it with our shear flow. And as a result, we get the ratio per line. When we deactivate the beam panel mode now, so this is a new feature, we will see also the graphical representation of the maximum ratio. So when we do so, like here, deactivate types for lines and maybe show only come on. It doesn't, or maybe let's do it like that. I will hide the lines. Yeah, okay, doesn't matter. Okay, good, but let's make some screenshot again and go to our presentation. I will insert here my screenshot and then let's compare. So these are the results here on the left hand side from the book. So we compare the ratio 84 by 88, 60 by 64, 65 by 58. Yeah, nearly 70 by 73, 13, 13. So of course, it's not perfectly the same numbers, but you see it is exactly, or in terms of FEA approach, we get exactly the same results. Of course, the results are not perfectly the same because in the distribution here in this classical calculation method, for example, sheathing edges are not considered. Yeah, it is assumed that this is one sheathing. Yeah, and of course in the stiffness it's considered, but not in the distribution of the forces. So, and that's why we get different, a bit different results, but it's still absolutely fine and okay. Okay, so this is yeah, another step, and we will come now to the end by comparing the results when we have some openings. For that, we will switch into our RFEM again, and I'm just thinking what we should compare. Yeah, maybe it's enough to check only this one here. Here we go. We delete this, and we will create a copy of this one. Uh, 15 meters should be fine. Okay, and now let's assume we have a window opening inside this wall and this wall. So this can be done as shown in my first webinar by using the surface cells. So what I will do now is I will place the work plane here at this location, and then simple use the grid points. Here we go. So I will create the opening from this grid point to this grid point, and then let's copy the opening to the next wall. Here we go. And now we need to define the opening because, as you can see, the studs are not considering it. We need to create, we need to create cells first by defining surface cells due to the opening in Y direction. It creates automatically this line, and now, yeah, the opening is perfectly considered. Okay, so what's happening, or what do we expect now? Yeah, so we have two walls with openings. That means these walls are weaker. The ratio of this wall, I check it in the PowerPoint on my second monitor, was about 70%. Yeah, so there is still capacity left for this wall to overtake these forces. Yeah, and yeah, let's see what's happening. So I expect, of course, these four walls cannot take, or these walls here cannot take so much force, and the forces will be redistributed here to this and this wall. Okay, let's check. Okay, let's check top view. So when we compare the forces, is exactly as I said. So here we have no openings. The forces are higher than here, and the wall, the interior wall here, with 15.2 kilonewton versus 19.4 kilonewton. It's exactly as I said, or as it was expected. Yeah, we get a redistribution of the loads, and also about the deformation. Yeah, we have weaker stiffness here. We get, of course, much or a bit weaker overall structure compared, yeah, say 10 by 13 millimeters or 10 over 13 millimeters. Okay, so when we think about openings and in terms of hand calculation, so what is done? Yeah, I will create again a copy of this in practice. So by 30 kilonewton, 30 meters, here we go. Okay, so when we think about Eurocode approach, so it says we cannot consider the elements for the openings. So we have to check the part left and right to the opening only, but you can imagine this is only 50 centimeters. You get extremely high forces inside. Forget about that. So what is done in practice, these walls are deleted completely, yeah, because it cannot be considered for the bracing. When we do so, let's run the analysis again. Of course, the deformation should be much, much higher now because we miss a lot of stiffness. We had 25 kilonewton on both walls. This needs to be transferred to other walls. Yeah. Okay, so let's check the deformation first. It's 9.6, 12.7, and now nearly twice as this one with 28 or 29 millimeters. Of course, that's clear. And we check the forces. So yeah, you see here we had 20 kilonewton. Now we have nearly twice as much. We have 40 kilonewton, which this wall needs to be covered. Imagine the hold down forces here. Yeah, this is crazy. So yeah, I would not try to cover it because the forces will be really high. Yeah, and also the deformation, yeah, is too much. All right, so that's why our opening or our method with the beam panel and this opening approach, this FEA approach, is perfect for an economic design. Yeah. What we also can do now at the very end is, for example, yeah, let's do it here. Or no, let's copy it. Let's copy it again. And we think about to add some additional sheeting here on the other side. So what I will do is I will copy the beam panel 5 and I will assign another sheeting on this opposite side. And additionally, I will create a copy of the connector, and the connector spacing here we will reduce by factor 2, so to 40 millimeters. So now we have created a much stiffer wall here at this location. And then let's check out the results. Of course, higher stiffness, and you will attract more forces to this wall. Okay, so let's check the forces again. Yeah. Oh shit, yeah. Sorry. I forgot to assign the new thickness type to this wall. Okay, last calculation for today. Okay, and it is, of course, as expected. Yeah, this wall attracts more load, and yeah, dependent on the stiffness, you see the influence. Yeah, so it is the great advantage, yeah, to play with these values. Yeah, to not be dependent on this classical distribution of the forces, which does not consider the stiffness and the openings. Yeah, and of course this will, as I mentioned already, help you to get an economical result, economic result. Yeah. Okay, maybe deformation. It's the same. We have more stiffness compared to the center. Of course, less deformation as expected. Okay, good. Then that's it for now in RFEM. Let's switch to our last slide. It's about the outlook. So really soon we will release the Canadian beam panel design according to the CSA 086. Then we plan to vary the connector spacing within a surface. So that means studs at or studs with no sheeting edges we'll get some less connectors compared to sheeting edges with compared to studs with free sheeting edges. Then another hot topic are the gable shear walls. So here trapezoidal or triangle shapes should be implemented soon. We will start soon with this implementation. And then custom stud location and cross sections should be allowed in the future. Wall-to-wall connections and wall-to-floor connections in a proper way. And of course, I will continue by creating content for the webinars about timber shear walls. So we began in January with this small webinar about single walls. Now we have extended it to multiple walls. The next webinar maybe will be about diaphragms, will be about diaphragm design or multi-story buildings and so on. There is much topic or enough topic to give you further information in the future. And at the end, the big aim is also to define the shear connectors and hold downs and design it with our add-on components. All right, so that's it for today. I hope you have enjoyed it, and if there are any further questions, feel free to shoot us an email. Okay, perfect. Then I wish you a nice rest of your day, and I will hand over to Andreas. Goodbye.
Thank you, Gerhard, for your presentation. At the end of the webinar, I have additional hints for you. For example, our online courses. There's the RFEM 6 course. That's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design with RFEM 6. The Eurocode 3 course for the steel design. The Eurocode 5 course for the timber design. And the Eurocode 8 course for the earthquake design. And additionally, the AI masterclass course for the using of the artificial intelligence. You can find more information and prices when you click at the links here or scan the QR codes. You can get an RFEM or Eurocode course for free when you submit your customer project, and when we have published it, you can submit your files when you scan the QR code or click at the link here. Also hint to our free online services. Whereas, for example, the Dlubal community, you can ask questions there, and our support team or our users will answer you. You can determine wind, snow, and earthquake loads with the GeoZone tool. You can determine cross-section properties. You can download 3D models, for example, as a template for your project. And you can download the free trial versions of RFEM 6, RStab 9, RWind 3, or RSection. You can find more information on our website, dlubal.com, for example, the recorded webinars, knowledge base articles. You can ask our AI assistant, Mia, all the time, 24/7. Just try it. Okay, that should be also all from my side. I thank you for your attention. Thanks again, Gerhard, for your presentation. I hope we meet each other in a future webinar. See you then. Bye-bye.